bottom, you should be able to record. Yeah, perfect. There you go.
Okay, yeah. Hi, yeah, welcome to this quick discussion on how my experience with teaching engineering studies. And this is on the screen now. This is what I hope to do in the next hour. First of all, I'll just go through the resources that I use in teaching engineering. A bit of background information. When I was teaching full-time, I was head teacher at Corpus Christi Senior College, which I started up, and we eventually started engineering studies there in the second year, and throughout the 90s, we were the biggest centre for engineering for many years. We had over 50 students in year 11 and over 40 in year 12. And I'd just like to go through the methods that I use to generate that interest in engineering studies. I'll just go through how to develop interesting and informative lessons, vary the presentation. It's really important to have fun in lessons, and I'll explain how important well-ordered study summaries are. Then I'll just go through these. These are the resources that I'll explain that I use in a minute. Then I'll go through the 4 steps that are required for effective teaching. And then I'll explain how I keep my students on task. My online students, I'm teaching with Lismore Diocese now at the Online Education Centre, and I'll explain this, how I keep them on task. And it's not a bad idea. I used to use this when I was teaching full-time as well. And then I'll just go through the importance of the HSC, what I tell my students, because their performance in the HSC is extremely important. And the examination techniques that are really important to use that I've found from over 30 years of marking the HSC. Then, if we've got time, I'll go through. A lot of students have trouble with graphics, getting them done in time. I'll show you quick methods of doing graphics. And then if we have time, also I'll go through how to do friction on inclined planes questions in a fairly easy method using the 3/4 rule. Okay, I'll just okay.
I don't know why it's not letting you go to the next one. You might have to maybe take it out of full screen.
Sorry, what happened?
I'm not sure. Are you PC or Mac? Is there a set of arrows in the bottom left corner when you
it's
mouse
the
over
Mac.
in there? Oh, there you go.
Yeah.
Yeah.
Yeah. Okay. Right. Is that right?
It's on lesson slide and book annotation.
Yep. Yeah. Okay.
Yep, cool.
Okay. So let's. This is how I used to teach engineering. So the students would walk into the classroom. They would have their engineering studies book, this engineering studies book, and the slide that I would use, sorry, I've jumped ahead. I just want to explain these resources first, then I'll go to that slide. So this is DVD number 1. This is the one that I was using, I was just showing you then, and this is related to that book there. So I use this DVD to provide a colourful, informative presentation of my lessons. This DVD here does the impacts with the books, and this DVD here is the one where I've selected a whole lot of problems that the students find difficult to work out, like friction and inclined planes, method of sections. And so the students, this is normally in the library, and students can access this if they have trouble with any particular problem. And this is a graphics book. This DVD shows all of the solutions to the mechanics questions in that book. And then I'll go through this book later on. This is the fourth step in my teaching. And these DVDs here, these were done by a guy in Melbourne, a metallurgist, and I got together with him, and he's put little 5-minute videos on industrial processes, so that you don't have to keep changing, you know, videos, programs, and you don't have to sit through one or half an hour of a video. Anyway, I'll explain that now. So here's the DVD number 1. So I'm just going to explain how I teach shell moulding, for example. So the students come into the classroom, they sit down and they open up this book, and I tell them to open up at Shell Moulding, and then I hit that link and up comes this here. And this is on page 56 of the book. And then I go through and explain the process of shell moulding. And it's really important for the kids to be able to draw the process of shell moulding or any industrial process. Because the question could ask, list using a diagram the stages in the production of so-and-so. And so I go through that, explain it to them, and this is shown up through the data projector. It's colourful, and it's, you know, the technical savvy kids now really require something like this, colourful, in the teaching process. And so this is a part of the book that the kids have open, and you can see that all of this, we've done sand casting first, then shell moulding, then the next one will be investment casting, and then die casting. And all of the videos that I'll show you in a minute are in this order here. So you just keep pressing play and stop and so forth. And so while I'm going through this, I'm getting the kids to annotate the book. So I get them to highlight the heading to indicate that we've been through it, because when they study this, they want to know whether they've been through it or not. And then I get the kids to annotate it so that this becomes their study summary, so that this is the only thing that they will study from. And anything that's not in the book, they annotate down here. So I say no grain flowing casting, and you know, turbine blades and prostheses may be either forged or investment cast. And so that's the added information that I get them to annotate in this book. And by the time they've finished the course, this is their study summaries, because you know, girls are much better at developing study summaries, but boys are hopeless as far as I've found. And it's really important for them to get a decent study summary. And the reason why I wrote this book, I'll tell you a quick story on it. In the late middle 80s, I used to teach at Erina High, and I used to give copious amounts of notes. And one of the students who I had, I was walking down the steps with him, a very good student. I used to teach him in the Clerk of Works too, structural mechanics, and he's a good friend of mine. Anyway, he tripped on the bottom step and his folder just blew open, and it was a windy day and all of his notes were blowing all over the playground. So I thought, I've got to do a book. So that was in 1985. I started writing the book so that the kids can have comprehensive study summaries. So when we've done that and the students have a good grasp of this, I use these resources, a lot more of these resources, but I'm just showing you a couple of them. And I get the kids, I call these look, touch and feel resources, because you want to try and get as many senses responding to the learning process. You know, you can get sight, sound and touch responding with these look, touch and feel resources. And I get the students to feel how smooth this turbine blade is, because that's been made by investment casting. This prosthesis, and I explain that no further machining occurs here, and they're actually touching it. And this here, this is a demonstration of a tree. I show, but this is aluminium, and I deliberately show them this because you can see that it's got the sand texture on the outside, whereas this here has got the texture of a permanent, very expensive metal mold. And so they feel that, then they feel that, and you know, they're learning all the time. And this is an example here of primary piping, and I show them what primary piping is, how it's caused, and then and then they realise that this is cut off here on the bandsaw, and then this is remelted. So it's really important for the students to actually touch these things. And when I go through the practicals that I used to give them, I'll explain how to make it a fun lesson. Then after they've had they've felt all these and they've looked at them, we hand them around the class. I go to this DVD that's loaded in my laptop, and I go to casting, and then I go to that value there, and then I show them hang on, where is it? Investment casting, there it is, investment casting. I go to this queuing point here, but I would have shown that before, so it's all set up. And then I give them a 5-minute video on an up-to-date investment casting process. So we're getting all of the senses responding to the learning process in class. And they've had a whole lot of different instruments in that one lesson, so they don't get bored. And it's really important to set your classroom up so that it's interesting. So when the kids walk in, they can see it's a technical classroom. Like I used to change these motivational sayings every week, and the kids would always see, like I'd have out the front, tough times don't last, but tough people do. And it's amazing, year 11 and 12 kids, how they, if I didn't change it, they'd be looking for the change, or and they'd be asking, you know, for that. So it's really important to set the room up with really technical aspects, so that it does look like a engineering studies classroom. Now, I'll just go through the practicals. I'll go through the practicals after this. And then when I've finished a unit, I'd go to this book here, and we'd spend 2 or 3 periods doing all of these questions related to what the unit involved. And so this book here, they get experience with multiple choice, which is the first 20 questions in the engineering studies paper. And then they do extended response questions down here, and all the answers are in the book. And it's really important for the kids to have these answers, because it's a very good learning process to work your way back from the answer. And it's a very effective way of learning. And then I'd be just wandering around the class, helping the students to help them explain how this answer here relates to the question and so forth. So that'd be about 2 or 3 periods. And then at the end of the unit, I used to give a practical, and these are the sorts of things that really stimulated the interest in engineering studies when I was teaching it face to face. Like, and the fun aspect, like, for example, when I was teaching, for example, toughening of glass, strengthening of glass, and on the back wall, I had my laminated windscreen from one of my cars when it had a crack and it was replaced. And I mounted that windscreen up on the back wall. And when I was explaining how glass is strengthened, I'd go down the wreckers and I'd get a side window off a car. They'd just give it to me. And then I'd have all the students standing around in the room with safety glasses on. And then I'd put the window on the bench on a towel. Then I'd put a fairly heavy towel on top of the window. And then I'd get a wooden mallet. And then I'd ask a student to only hit it with 50% of his power, because we don't want, you know, the thing to explode. And anyway, he'd try and break it with the mallet. And then he couldn't break it. And then I'd give him a bradawl, and I'd just get him to hold the bradawl on the window, on the glass, and then tap it, and the thing would explode. And then I'd be able to explain that it's been thermally toughened. The outside layers have been in massive compression. And when you exceed that compressive strength of the outer layers, the energy is transmitted to the rest of the glass, and it just explodes into small, harmless pieces. And then, you know, I'd explain I'd explain how thermal toughening is done, and then chemical strengthening. I'd explain how the Gorilla Glass in an iPhone is made with substituting the small sodium atoms with potassium atoms in the outer layers, and which puts the outer layers in tremendous compression, and it makes it hard and very tough. So they're the sorts of things that I'd demonstrate. And now the difference between the fracture pattern of the thermally toughened glass and the laminated glass, I used to have a 25mm ball bearing. I used to get one of the kids to throw it, not too hard, but throw it at the windscreen that I've had up the back wall. And then you'd see the fracture pattern. It would hold together, and then I'd make sure that every student would go up there and with his fingernail feel the crack on the outside, and then I'd get them to try and feel if there's a crack on the inside. And there wouldn't be a crack on the inside because the PVB polymer between the two layers of glass has held it together. And then they've used that experience, and then you can explain crack propagation and how the polymer prevents the cracks from propagating through to the inside layer. Of course, if you put too much energy in the system, both layers would crack. But it's really important to show that. And when I go away, I obviously can't take a windscreen with me. I just got two slide glasses, and just put silicon between them and joined them with the silicon, and just fractured one side. And then I get the students to use their fingernail to feel the crack on one side, and there's no crack on the other. And then you've got enough information to explain how the crack has been inhibited by that polymer layer between the glass. But look, I'll just quickly go through these practicals. These practicals, they used to only take no more than 1 week, but they are extremely valuable. Like when we did forces, with the introduction of mechanics and materials, I used to get the kids to make up a bracket. They'd go into the workshop, make up a bracket, and then they would have to design this strut. And of course, lots of students would, you know, put the strut down here stick it out there like that. And then I'd either weld it. Yeah, that's what I used to do to save time. I just used to weld the strut on, and I didn't tell them how to position this strut or anything. And when the students put it on the flat, it failed very quickly. But the students with a bit of nous, they twisted it to increase the toughness of it, and then they had to get this screw in, because I had an apparatus here where the bracket would be inverted, and then I had a proving ring here to test how much force it would take. And when you get plastic deformation at that screw there, that's a good indication of what plastic deformation is, because they're actually seeing it. And they record the force that it took at plastic deformation, and they had to just briefly write an observation of what was wrong with their strut that they designed. Really important practical exercise showing how forces react. And I made it this shape here because the design of this was to hold up a dryer, and I had a frame there. And the first thing we do is put the bracket there and see if it would hold up the dryer. So that was the original aim, and then we'd test the two destruction on this. So the students could see forces in action. And also we used to use the tensometer. I used to get the kids to lap their own samples after they've been broken. This activity here, ferrous and non-ferrous, this is how to change the properties. I used to get 0.6% carbon mower blade and show them how hardening and tempering works. So 0.6% carbon, and also I'd have a 0.1% carbon piece of steel. Heat both of them up to red heat, and then I'd quench it, and then I'd get all the students to stand up on the benches with eye protection on, and then I'd throw the mower blade on the ground and it would shatter because it was wholly Martin City. And I'd throw the 0.1% down, nothing happens to it. And then I'd put both of them in the vise, show them that the 0.1% isn't affected by heating and cooling, and the mower blade, put that in the vise and you just tap it with the hammer and it would fracture very easily. And I'd just say, you could just imagine if mower blade in this condition was put in a mower, it would just fail with the first rocket hit. Then I'd get the mower blade a big part of the mower blade that actually fractured on the floor, and then I'd shine it up, I'd temper it, allow the temper colors to come up, the brown temper color to show that it's fairly low heat, and then put it in the vise and it would be tough again. So they're the sorts of demonstrations that really cement ideas and knowledge in kids' minds. In fact, that student I was telling you about who I taught, I met him last year sometime, and we were talking, and he was saying that he can still remember the difference between thermally tempered glass and laminated glass from the demonstrations that he experienced. So it's a very effective way of learning. And it's fun too. Like this one's a really fun one. I used to get the students to design a mousetrap car. And I had light gates here from the science department, and I had a local mob make up a channel out of stainless steel. See, this is the channel here. Or what you can do is get a rectangular downpipe and cut the one face off. And then they had to go between the light gates, which were 20 meters apart, in the shortest possible time, just using the energy of the mousetrap. And here's another one that I used to do. I used to have a fan here, and they had to design a car that would have its motion towards the direction of the fan, which is against the air direction. And they used to get in groups of 3 and design these cars to do that. And that's when we were doing motion. This is corrosion. We did practical on corrosion, but this is the one that really stimulated interest. I used to do the testing of trusses in front of the whole school, and what the students would do, they'd have to design a high specific strength bridge, which is according to these dimensions. You can't just say design something. Anyone can design a strong structure, but you've got to limit the dimensions and you've got to limit the mass of it. 22 grams. I mean, just a whiteboard marker is 17 grams. So they have to really do the design of this intelligently. And I had an articulated roadway across the top there, so that didn't take any force at all. And then we had this little, we call this a little truss buster. And we had a box on the front, and the kids used to load their masses on there, and it had to go across and back. And then if it didn't fail, that's the winner so far. And then one of the other kids would up the mass and then try that. And the good thing about this is that they've worked out, I show them how to work out the forces in all the members, and they know which one is the most highly stressed member. Just say that one there is the most highly stressed member. And I got them to paint that, just use a red marker and show which is the most highly stressed member. And we get the students to watch when it's just on the verge of failing to see that that is the one that lets go first. And generally it does let go first. So they're relating their mathematics to actual what happens. Yeah, that was a very successful one. And making electric motor, that only takes 3 periods to do. Testing different samples of polymers to try to identify them using this flow chart. Making up with slip casting, they can work out what the percentage porosity of this is. That's a simple method of seeing how porous glazed and non-glazed ceramics are. And this one here is when we did bending stress. The idea is that I gave the students a 20 by 20 millimeter piece of wood, which is 300 millimeters long. And we tested that and worked out what force occurred when it failed. And then I wanted them to make it into a laminated section and see how they can enhance nature by laminating the timber. And each of them were tested, and they had to achieve a higher force for theirs than what the natural timber achieved. And this is pretty easy. You just make a proving ring. You put a dial indicator on the inside there, and then you put some gym weights on, and then you can calibrate what the force is. This is just a bit of steam pipe that you can cut, and it has to have around about 0.8% carbon so that it makes it fairly tough and elastic. But you can buy these also. Okay, so there are the 10 practicals. Now what I want to do is just show you how I keep my online engineering studies students on task. So these are all their names. Each week I give them a CWR, I call it a compulsory weekly revision. And so this takes a fair bit of time, but it's well and truly worth it. I was telling Tony the introduction that, you know, I was only getting 30–40% response. But since I started this, and every 2 weeks, I send this record of how they're doing their weekly assignments, their tutorial attendance, and their lesson viewing. As soon as I send that every 2 weeks, I send it a copy to the parents, to the mentors, and to the students. All of a sudden, we got quite a good response from the students. And I use this. This was, as you can see, 18, 19. These two students, that student there came second in the state, and that student there got the same mark. So it just shows you how they break it up into decimals. He came ninth in the state. And I just use this to show how this is when I do revision. This is all revision towards the end. And I just show them how a diligent student achieves their potential at the HSC. And you can see here, this person, he was diligent all the way through, and he achieved his potential at the HSC. Whereas the others, you can see the result of inactivity. So it's really, that's how I sort of motivate the students. And if it's pink, they're late viewing the lesson, I expect them to view the recorded lesson by 2300 on Sunday. And if they're late, they get a pink. So it's really, I've got to be as diligent as I expect the students to be. Pardon? Okay, so that's how I keep my online students on task. And this is, I'm just going to go through how important the HSC is. This is what I give my Year 12 kids. This is the school assessment here. You can see what the aggregate is. And then this is their examination mark. You can see that they went better in the exam than the assessment. So the moderated assessment is given the same aggregate and the same mean as what the class achieved in the exam. This is why, if you've got a long tail, it can really pull your results down. And you notice that student B here, he didn't go as well as student C in the exam, but the rank stays the same. But look what happens when you get the HSC mark. So student B has jumped down to 3 and student C has jumped up to 2. So I use this to tell the students that, you know, you've got to do the exam as best you possibly can. And I've got exam techniques that I'll go through with you, and so that they can hopefully achieve their potential in the HSC. These were my marks 1 year, and I just showed them that the aggregate for the marks here were 494 for their exam mark, and they went better in the exam than their school assessment, and that's how they moderate the assessments. Now, how to answer questions in the HSC. It's really important that you explain this to the students. The worst thing that my students do when they're answering these impact questions is they repeat the question, which is just a waste of time. Make sure you tell them not to repeat the question. And this response here would achieve 0 marks. Describe means to provide the characteristics and features. And this statement here doesn't do any of that. And you've got to make sure that you qualify a statement. if you're describing something. If you just state convenience, for example, here, this is the way that I get my students to answer these effect questions. You've got to, I ask them to give positive effects and negative effects. And generally, we only require 2 positive and 2 negative. They won't tell you how many, but I just say 2 positive, 2 negative. And if you just write down convenience, you won't get the mark because it's asked you to describe. And you've got to put conjunction in. You say convenience such as blah, blah, blah. You've got to qualify your answer there so that you get the described marks. And so this is what I try and get my students to do. It's the method of answering shown above is very appropriate for engineering questions. Answers should be straight to the point. I like these straight to the point answers here. Doesn't matter if we can't mark them on the spelling or the punctuation or anything like that. We're looking at keywords. Show both positive and negative if the question asks the effect or impacts. I like them to be presented in a list or dot point form so that you know, it's quite easy to mark and to see that you've answered the question correctly. And only give the type of response such as describe, compare, explain, or outline. Don't go off into any tangent, because if you don't do that, you won't get any marks and you've wasted your time doing that. This is what I get my students to do. I tell them to divide the time for the examination by the total marks to determine the number of minutes per mark. Now, for engineering studies, that's 1.8 minutes per mark. And so I tell them to multiply the marks by 1.5. And so that if the question is worth 10 marks and they start that at, say, 10 o'clock, I write 10:15. I get the students to write 10:15 at the beginning of that question. And so they work their way through. And if they don't finish that question within a minute or two of 10:15, I get them to put a star against the question so that the 1.5 minutes will give them 30 minutes to go back and complete that question. And there's a lot of evidence to indicate at the end of an exam, they're more intelligent than the beginning, because they're more relaxed and they're not stressed out. And there's more than, it's quite likely that they'll be able to answer that question in the 30 minutes. And this is for this reason here. So if you go to spend the last, so this question's worth 5 marks. So that'll be 7.5 minutes for this question. And if you go over time and spend an extra minute on that question, that's how many marks you can gain in that question. But you start the next question, look how many marks you can gain in 2 minutes. You can gain more than half the marks, because you're indicating how you're going to answer that question, and it's a valuable way of doing examinations. And so if you have to go over time, put a star next to that question and come back to it when you're finished the exam. Now, what I want to do is show you how marks in an exam can indicate what sort of responses are required. So see this question here with reference to the 2 Qantas planes. If you don't refer to this here, you're not going to get maximum marks. Describe 2 historical developments in the aeronautical industry and provide 2 examples. So for the markers to mark this reasonably, because we're not allowed to use half marks, so the description of a historical development will be worth 1 mark, and 2 examples would be the other 2. And there's 2 historical developments, So twice 3 is 6. So there's 1 mark for that there, and there's 1 mark for that there, and 1 mark for that there. Okay, so that's, and here's historical development 2, 1 mark for that, and 2 impacts down there. So the students should be aware that there should be 6 responses. And I want to draw your attention to this here. See, that demonstrates some knowledge of the question. You get 1 mark. Have a look at this here. I had a student just do this. Now, he hasn't demonstrated any knowledge of this question here, but I get my students to write down the formula and put the data down here with the correct units, so that if this student gets the wrong answer here, the marker goes back through and he's shown a lot of knowledge of the question. So you'll get marks for this, you'll get 0 marks for that. But more importantly, if there's a mathematical error here, you can't see what error is there, but we can pick a mathematical error here. And if he's made, if this is section part B of the question, and he's made a mathematical error in part A, you can't double penalise him in the same question for a mathematical error. So he can get full marks for a wrong answer. If he sets it out, he or she sets it out so that the examiner can actually see where the mistake was. You can't see that there's a mathematical error there. Okay, now what I want to also show you on a truss is this. See those marks there? That indicates that it's not a difficult question. If it's 4 or 5 marks, it's going to be fairly involved. Now, what they're asking here is for the student to find the force in member A. Now, you can, I'll just see if this works. I'll just try and annotate here. Yeah, so we're going to put a section there. Tell your students not to just do that. Make it a section, and not which is a chain line. And so you have to find this reaction here, right? We'll call that reaction right. Okay, and so we'll call that reaction left. And this, lots of students did this. They say the sum of the moments about reaction left equals 0, with that direction positive, and then away they went. So they did RR times, now remember you've only got 1.5 times 3, which is 4.5 minutes to do this. So you've got RL times 3, 6, 9, 12, 15. And that's going anti-clockwise. Then you've got 2 times 1.5. And you can see what's going to happen. That's positive. Then you've got this one, that one, that one, that one, that one. And 10 minutes later, you've found the right reaction, so that you can take moments about this point here, and then you can find the force in that member. But it's taken, 10 minutes to actually, or 5 minutes or whatever, to find this reaction. But when you've got to tell your students that when you can see that this is going to take you too long for this mark here, you've got to look at it and see how you can do it in a much easier way, because the marks are telling you you're doing it the wrong way. So I'll just undo all that. And so you look at it and you see that it's symmetrical, and you can do it in your head. And so you've got 2, 4, 6, 8, 14, 26, 32. It's symmetrical. 32 divided by 2 is 16. So you just put 16 down here, and you don't have to show any working or anything like that. And I'll just show you the examiner's solution here. No working, he's just put the 16 there. So make sure that you know how to look at the marks, and I'll just try and get rid of all this. I'm not used to this. And then judge your response from the marks there. I'll just go through this method of sections because lots of people have trouble with the method of sections. I'll just go through a bit of theory about it. So we know that that up there is 16 kilonewtons. And we're going to section this. We're going to take a section through there. You can take a section through 1, 2, 3, but no more than 3. And I tell my kids that I've got a big metal cutting chainsaw. I've cut this truss, and I want all of the left-hand side to fall and float away down the river. And I want this section here to stay upright. And I want it to be in equilibrium. So if I take moments about this point here, I know that the sum of moments about that point equals 0, but it's going to do us no good because we're going to end up with 3 unknowns in the equation, because I always say that they're in tension. So I'll just show that going there, that going there, that going there, and I put a question mark there, question mark there, because I'm just guessing that it's in tension. And so if I take moments about that point there, that produces a moment, that produces a moment, and that produces a moment. So you're going to end up with x plus y plus z equals whatever, 20. We're going to have 3 unknowns in the equation. So it's silly to take moments about any point, even though the moments about that point equals 0. So you've got to look around and see, we want to find this force here. I get my students to highlight that so you don't have to keep looking to see what force you've got to find. And so the mathematical gymnastics that you've got to do is you've got to eliminate these 2 forces here so that you can take moments about a point where these 2 forces go through. And obviously it's that point there. So if you take moments about that point, the sum of the moments about that point have to equal 0 because this thing's in equilibrium. And so all you've got is 1 unknown in the equation. And so that's the secret. Now you can take moments about that point, any point, even though this truss is no longer there, because you can take moments about any point of a structure that is in equilibrium, and the sum of the moments will be equal to 0. So it's really important to stress that to the students. The first place that you look for is see where the other 2 forces meet. And that's the point that you take moments about. Okay, I'll just get rid of all this. Lots of students have trouble with method of sections. Okay, and there's the examiner's solution there. Now, this was a question that I asked in one of the independent trials. And they're asking you to determine the force in the right reaction and the left reaction. And as soon as a student gets a question like this, I get them to draw, I get them to put this force in, and I get them to show that it's at 90 degrees. And remember that last one mark on the marking scale says show some knowledge of the question. I mean, if everyone's having trouble with this, that's sufficient to give you 1 mark. I just want to go through the 3-force rule. If 3 forces are acting on a body and the body's in equilibrium, the 3 forces will all pass through the same point and they'll be concurrent. So by the principle of transmissibility, and I'm just doing this freehand, you can just project that up there, project that up there, and where the 2 forces meet, there's our point of concurrence. And so this force here has to go through that point. Now, you know that this force is going down there like that, and we're not quite sure whether this force goes up or down, so we'll give that a miss for a while. Now, this is called a free body diagram, and it's not a mathematical diagram. The only mathematical diagram will be the force diagram when you apply a scale to it. So I'm going to work out a scale here and make sure you get your students to show where the scale is. It doesn't take long to write scale. And the rule is that if you put your second finger and your thumb together, see the hole that's made in if your force diagram will fit there, it's too small. So the rule is that you get the biggest force, which is 100 kilonewtons there, and you make that equal to between 30 and 100 millimeters. And so I'm just going to say 100 kilonewtons equals 100 millimeters. And so I always get my students to break it down so you don't have to think, you don't have to divide anything. 1 kilonewton equals 1 millimeter. Okay, so there's the scale. Then I use Bose notation. You will never be examined on Bose notation because it's a technique. And make sure that you letter between 2 forces going in a clockwise direction. Can't go anti-clockwise. If you do that, you're saying 2 plus 2 is equal to 5. You're going against convention. And so there's B and there's C there. And then now, can I change color? Yeah, I can't, I don't think. Oh, yes, I can. Yeah, okay, so I'm just going to, this is the known force, so I'm going to draw this 100 millimeters long, put the sense on it because it's shown, and this force is CA. C is the tail, and A is the head of the force. If you do this, it's just like joining the dots on a donkey. Okay, so you go clockwise, and so the next force is AB. You transfer that angle. You know how to do that with set squares, and we don't know whether it goes up or down. I'm just going to try and draw it parallel here. We don't know. Now that force is a, so we've got, sorry, this is force CA. Sorry, that's wrong. So this force here is CA, so that's force, whoops. That's force CA there. And so the next force is AB. It's got to go through A. And so B lies somewhere along here. And then we have to leave that. And so the next force is BC. And there's C. And so that point there has got to be B. And so all this sense here tells you, because it's in equilibrium, tells you what sense all the other forces are. And then that is, this here is a mathematical diagram. So you can just scale off these lengths. And with a simple diagram, you've got the solution to a fairly complex question, right? 4 is getting up there. And so using the 3/4 rule, you'll be able to do a simple solution. Now, I'll just remove all this. So the 3/4 rule gets students out of a lot of trouble. And so you can see, yeah, I mean, this is fairly advanced maths over here. And there is the solution. There's our force diagram going down there like that. And the good thing about graphical solutions is that you can, I'm a bit slow. I want to try and finish in an hour if I can. The graphical solutions, they'll give you 10% error in the exam, in the HSC. Okay, this question here, I was just going to go through and show you how the question leads you into the answer. And you can see that these are two fairly simple sorts of questions with the marks here. So you've got to find the force in member CE here. And so there's CE. I'll get my students to annotate it. And so for the second part, you do a section here. And obviously you take moments about that point there. So if any student worked out what the right reaction is here, it's a waste of time, because you'll work out the reactions for one. So that reaction will go there, and this reaction will go up there. So if you take moments about that point there, you don't need that reaction there. So it's a waste of time. So you can see how the examiner is leading you into taking the left-hand side to work out the force in that member there. Because all you do, if you're taking moments about that point there, you've got that force, you haven't got that force, and you've got that force, and you've got that force to contend with. So make sure that the students are told that the examiner can lead you into the correct method of doing it. So don't find any forces that you're not asked to, if you can help it. Okay, I'll try and be quick now. I won't have enough time to do friction. So there's the solution to that question. So we haven't found the reaction in H. Now what I want to do is just quickly go through graphics and show you how to do graphics quickly. Now the idea is that we're not trying to teach the students to be CAD operators. All we're trying to do is to teach them to do in situ drawings, so that a young engineer walks into a room, sees a bracket up on the wall and thinks, oh, I can modify that. And so he or she draws the bracket and then gives it to the CAD operator to make a working drawing from it. So here, this is a question that was asked a few years ago, and I deliberately put this here to show you that this is inaccurate here, oh, this is incorrect here. See how they've put that hexagon as a chain line there? And the examiners do make a few errors occasionally. So tell the students that if you know that there's an error here, don't get stressed out about it. Just, even if you just put on it, is this correct, or something like that. When it's marked, that's taken into account. So don't stress on it. Now, this is 6 minutes to do that. You'd have to be pretty good to do that in 6 minutes. This is how I used to mark them when I had big numbers. I used to just go through the papers and get sample answers and allocate a mark to each one. And I'd have this beside me so that when I'm marking, I can be fairly consistent. This one here where you've got an exploded isometric to do, this is how I marked this one. I said that 12 to 13 points. I isolated 13 points on this diagram that should be marked, and then that's how I broke it down, because you're not allowed to use half marks at all. And then, so this was 0 marks, and then it goes up to 5 marks there. So you can just see your consistency. That's when you've got lots of students. Now, finally, I'd just like to show you how to do a graphic in engineering HSC exams. The first thing, if you're transferring an orthogonal drawing to an isometric, I usually do this in term 1 with my year 11s, and then in term 2, I convert a pictorial to an orthogonal. In term 3, I actually sit down and show them how to do it in 6 minutes. This is the way that I do it. I use set squares where I get these angles fairly right. I've just done this freehand here. If you're good at freehand, you can do it. But I usually use set squares to get that box, the initial box, correct. And then I write on these here, I measure them all, because it doesn't have to be, exactly accurate. A solution like that will get maximum marks there. And then I just put all the sizes on here, the sizes that I need. I just write the sizes on so that you're not continually measuring this. So once you've done your box, you get rid of your set squares, and then you just put all of the other lines in. If you still want to use your set square, that's okay. But if you've got these lines fairly accurate here, you can just do these as partner lines. You can do it freehand if you like, because they're in situ sketches. Then you do the circles. Now, make sure that you know that isometric circles are oriented according to the faces. If you just do a circle there that isn't oriented, you're going to lose marks. So see, you got a face upwards to the left. It's the circle, isometric circle has to be sloped upwards to the left. And then you firm it in. You don't rub out all of these lines, all the construction lines, because you want it to be fairly quick. And that's how you do these drawings fairly quickly. You can do it, as I said, you can do it freehand, or you can use set squares. But it takes a lot of practice to do these drawings. I'll just go through this drawing here. This is a bit rough. This, when you had to do a section, because this is symmetrical, the examiner said that this is the correct answer. It's not the correct answer. You don't have to section the symmetrical object on both sides. This should all be an outline. You don't section this here. That's the first thing I wanted to show you. The second thing is that, see the pitch circle diameter? you've got to show that in section. And the rule is you rotate it around the pitch circle diameter and you show it in section. So that's why that has been shown in section. So you rotate pitch circle diameters. And another thing that is really good to know is see where these flats on the hexagonal nut go. They go between the threads there. Now, normally you would be expected to do this, right? You set up your compass and you draw a semicircle like that there. And then using the radius, you mark there, you mark there. And so you've got your hexagon drawn, but it takes too long. See that line there? That will always go between the threads there. So don't waste time doing that. Just put it between the threads. And make sure that you know, you can see what they've done here. They've just shown this view showing two faces there. Deliberately, they've done that. If you show through two faces here, you'll lose marks, because the rule is if you haven't got another view that shows that that's a hexagon, you've got to show three faces there, like I've shown here. And look, here's a technique that they use to mark it. See that there, that boss there is 40 millimeters diameter, and this here across corners is 1.8D, which is 36 diameter. And as soon as we're marking this, as soon as you see that difference there, you know that he's got the nut correctly done. So there are a couple of things to think about with the exam. And I haven't got time to do the friction. So
that's all right.
Yeah.
Thanks for taking us through everything this afternoon. There was a question in the chat, and I haven't been able to open the file, but I have a question